Intel built its dominance on controlling both chip design and manufacturing, which allowed it to lead the industry in performance for decades. Its process technology consistently stayed ahead, enabling smaller, faster, and more efficient chips compared to competitors. This leadership created a system where Intel dictated the pace of innovation across the semiconductor industry. However, as manufacturing complexity increased, maintaining that lead required near-perfect execution at each new process node. The transition to 10-nanometer technology became delayed repeatedly, pushing timelines years beyond original expectations. While Intel struggled to deliver, competitors like TSMC advanced to 7-nanometer and then 5-nanometer production. This shift allowed companies such as AMD to design chips that outperformed Intel's offerings, using more advanced manufacturing. The advantage Intel once controlled began to erode, not because demand disappeared, but because execution fell behind. This marked the point where a company built on process leadership faced the consequences of losing it. Intel's rise was built on the x86 architecture, which became the standard for personal computers and enterprise servers over multiple decades. The company's Intel Inside strategy established its processors as the core component powering the global PC ecosystem. By supplying chips to major manufacturers, Intel scaled rapidly without producing finished devices itself. Performance leadership allowed Intel to command premium pricing, which supported strong margins and consistent revenue growth. As computing demand expanded, Intel's processors became essential across both consumer and enterprise markets. The company's influence extended into data centers, where high-performance chips drove critical infrastructure workloads. This created a system where Intel controlled both the design and production of its chips, reinforcing its market dominance. At its peak, Intel dictated the pace of advancement in semiconductor technology. At its core, Intel operated as an integrated device manufacturer, designing and fabricating its own chips within the same organization. This structure gave Intel direct control over process technology, which allowed it to optimize performance and efficiency at each node transition. Unlike competitors that relied on external foundries, Intel's vertical integration created a consistent lead in manufacturing advancement. The company followed Moore's law aggressively, reducing transistor size and increasing chip performance generation after generation. Each successful node transition reinforced Intel's advantage because competitors struggled to match its manufacturing capabilities. This created a feedback loop where better process technology led to better products, which increased demand and funded further innovation. High margins from this model supported massive investment in research and fabrication facilities. However, this structure also concentrated risk because success depended entirely on Intel's ability to execute internally. As complexity increased, the same model that created dominance began to require flawless execution to maintain its lead. Through the 2000s and early 2010s, Intel's growth was driven by sustained leadership in both PC processors and data center chips. Server demand increased as cloud computing expanded, and Intel's Xeon processors became the standard for enterprise infrastructure. This created a high-margin segment where performance and reliability justified premium pricing. At the same time, the company maintained its lead in process technology, moving ahead of competitors in successive node transitions. Intel's 14-nanometer process became widely deployed, supporting strong performance across multiple product lines. Revenue scaled with demand for computing power, which reinforced the company's dominant position. At peak performance, Intel controlled a large share of both consumer and enterprise CPU markets. This allowed the company to operate with strong profitability and predictable growth. However, maintaining this position required continuous advancement in manufacturing precision and execution. As process technology advanced beyond 14 nanometers, the complexity of manufacturing increased significantly, raising the difficulty of each new node transition. Intel's model required it to simultaneously design and fabricate increasingly dense chips, which compounded execution challenges. The transition to 10-nanometer technology introduced unexpected technical issues, including yield problems and production inefficiencies. These challenges caused repeated delays, pushing back product launches and disrupting planned timelines. Because Intel controlled its own manufacturing, these delays could not be offset by external partners. At the same time, competitors that relied on foundries were able to adopt more advanced nodes without managing fabrication internally. This created a divergence where Intel's internal model slowed progress while others moved ahead. The advantage of vertical integration began to shift into a constraint because delays affected the entire system. These issues built gradually, but they set the stage for a more visible loss of leadership as competitors advanced. By the late 2010s, delays in Intel's 10-nanometer process had extended for several years, significantly impacting its product roadmap. During this period, competitors manufacturing through advanced foundries moved to smaller nodes, including 7-nanometer and then 5-nanometer technologies. This allowed companies like AMD to release processors with higher core counts and improved efficiency compared to Intel's offerings. Performance leadership, which had defined Intel's dominance, began shifting toward competitors. In data centers, where performance and efficiency are critical, this shift created pressure on Intel's most profitable segment. Market share began to erode as customers evaluated alternatives that offered better performance per watt. At the same time, Apple transitioned away from Intel processors in its Mac lineup, adopting its own silicon based on advanced manufacturing. This represented both a symbolic and practical loss of influence in a key ecosystem. The system that once defined industry leadership had now lost its technological advantage due to execution delays. As the loss of process leadership became clear, Intel initiated a series of structural changes aimed at restoring its competitive position. A new leadership direction under Pat Gelsinger focused on rebuilding manufacturing capability and improving execution discipline. The company announced a multi-year plan to regain process leadership through accelerated node development, including new architectures and fabrication techniques. At the same time, Intel introduced a foundry strategy, offering its manufacturing services to external customers through Intel Foundry Services. This marked a shift away from a purely internal model toward a hybrid approach that combined design, manufacturing, and external partnerships. Massive capital investments, often exceeding tens of billions of dollars, were committed to building new fabrication facilities. These investments aimed to close the gap with competitors and reestablish control over advanced node production. However, this strategy required both time and consistent execution, which introduced uncertainty around outcomes. The system was no longer focused on maintaining dominance, but on rebuilding the capability that had originally defined it. Intel's trajectory shows that technological leadership in semiconductors depends not only on innovation, but on consistent execution at increasing levels of complexity. When delays disrupted its process roadmap, the company did not lose demand, it lost the ability to stay ahead of competitors. In response, Intel restructured its strategy by investing heavily in manufacturing, adjusting its model, and committing to long-term capability rebuilding. The introduction of a foundry business and renewed focus on process development represent attempts to restore its original advantage. Early progress has shown incremental improvements in execution and roadmap clarity, which has begun stabilizing the system. However, the gap with leading foundries remains significant, and catching up requires sustained performance over multiple technology cycles. The company's future now depends on whether it can consistently deliver on its revised process roadmap. This marks a shift from maintaining leadership to attempting recovery in a highly competitive environment. Intel is not rebuilding demand, it is rebuilding the capability required to compete at the highest level of semiconductor innovation.